Hi everybody, this video today is going to cover linear regression and modeling data. We're going to talk about a lot about scatter plots, and this page is found in the last page of your notes booklet. A scatter plot shows a graph in which the values of two data variables are plotted, and the pattern shows, that word was omitted, any correlation present. So you can look at the scatter plot and find out what the correlation is. That is, how are they correlated to each other? How are they related to each other? We can describe how much they're related to each other. Is it really affecting it or not? And the way we do that by using the correlation coefficient. And we use this letter R for the correlation coefficient, and it describes how closely the data points fit the line of best fit. So, for instance, here we have some points and they are just almost exactly in a straight line. Whereas over here, they're a little bit more spread out. And so when they are perfectly in a straight line like that, they have a really high value, a high correlation coefficient. In addition, we know that this is positive. The reason it's positive is because it has a positive slope. So if it's going up, it's positive. And they're really tightly together, so that's a high value. This one has a negative slope, and so it's negative. And it's still pretty high though. Like I can see a line forming here, right? And they're a little bit more spread out, but it's still pretty good. This one is positive, it's going upwards. Can you tell, even though they're really spread out, you can still kind of tell how the line would kind of go like that. But it's a lot lower. Like these are really close together. These not so good, it's not so close. So what I wrote down, you can hardly read it because I wasn't expecting that this would be on the screen, but it is that it's positive because it has a positive slope, but it's a pretty low correlation. See how spread out they are? And then this one, it's like you can maybe kind of make an argument that there's a line, but it's a really low coefficient. So I wrote down negative and very low. Negative because of the slope, and low because of how spread out the points are. Let's look at a couple more. This one now has a negative slope, but it's still really high together. And this one, I can't even tell. Like, where would you put that line? Would you say it's going like this? Would you say it's going like this? But I mean, who knows? So that one, I'm going to say, has no correlation. They're not related. Whatever we're plotting, it's not related. And then this one, again, it is positive in the positive direction, and it's pretty high. Like, I can see that line. That's a little bit spread out, but not too spread out. So that's pretty good correlation. When we talk about correlation coefficient, it actually has a letter, this letter R, and it is a value used to describe the strength of a correlation, and it ranges from -1 to +1. And this is like 100%. A -1 would be 100%, but in the negative slope, and a +1 would be 100% in the positive direction. And so this would be like a perfect line going upwards. When your dots are perfectly lined up in a perfect line going upward, that is a 1. If they are perfectly lined up going downwards, that is a -1. This is just a bunch of description, which I'm not really going to go into. And so these R values, they're between -1 and 1. If it is negative, then it's a negative slope, and it's a pretty high number. Like it's pretty close to -1. And so these are going to be dots that are pretty close together. This one, if it's 0, it has no correlation. They're not related. They're just random points. This one, it is still positive, but it's pretty low. So 0.3, it can go all the way up to 0.999 or even 1.0. So 0.3 is pretty low. And then this one is a negative, and it's also pretty low. And that one, anyway, we'll take a look at some other examples. Let's go back up here to the top and estimate. What would you say? And I would say this one, because it is just almost a perfect line, I might say it's a 0.99. You could even argue it's a 1.0. I don't know, but it's at least a 0.99. This one, it's going to be negative, pretty good correlation. I'm going to say about a -0.8, approximately. This one, positive, going up, but not very well related. I'm going to say more like maybe a 0.6, because it does still show a line. You can see a trend. This one, I may be a -0.6, kind of a same, right? They're similar, just this one's going up, this one's going down. This one, I'm going to say a very high relation, negative because it's going down, but about a -0.99. This one I talked about a second ago, I think it's 0. There's no relationship here. And finally, this one, maybe a positive 0.8. And in class, we'll go to a website where you can kind of practice and see if you know what the relationship is. And I really like this lesson because it shows us like the real world. Like, when are we ever going to use this stuff? This is absolutely things that we will use, because you can see, are they really related to each other? Then we could say that, exercise improves your cardiovascular health. Are they not very related to each other? Well, you could say, well, you took that, let's say you took that supplement. Did it really affect your health? Well, some people it did and some people it didn't. So that's not very related, but this one is related. Okay, on the next page, a line of best fit. And I think maybe you've done this before. A line of best fit is a line in a scatter plot that shows the correlation and trend of the data. So take a ruler. It's always good to use a ruler when you're doing a line of best fit, or a straight edge of some kind, and make a straight line here. And what you want to do is you want to try to make it kind of go through the middle, and show the trend of the data. So let me show you what I mean. Some people talk about, let's count how many dots are above and below. Okay, well, we could do that. I've got, the way I did it, I have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. Well, mine's not exactly the same number. But you know what? Take a look. I could say, well, maybe something like this. It has the same number above and below. Yeah, but it doesn't really fit the trend. Like, you want it to show what direction is it actually going. And so we do this, so it goes through the middle, but it also shows what direction things are going. That's the important part. And what this allows us to do is it allows us to make some predictions. So let's take a look at what we have. We have the data in the graph below shows the number of sales made and amount of money spent on advertising for 12 accounts in an advertising firm. So this is how many sales they made, and this is how much money they spent. Okay? So how much sales would you predict after spending $5,500 in advertising? Okay, first of all, this on the bottom, it says 5.5, but then it says in thousands. So we want to make sure that we understand what the graph is talking about. So when it says in thousands, that means like 5.5 thousand. That means 5,500. That one is right here. And this is one of those graphs. I don't love these kind of graphs, but sometimes you just have to do it because of what's going on. But they cut off part of the graph, right? And sometimes we show a little jagged line right there that shows that they cut off part of the graph. But at that time, at $5,500, if we look at our graph, it hits it on my line, it hits it right about here. I'm going to estimate that and just say, well, that's about 106. 106 what? I don't know, whatever they're selling. They're selling something, and they sold 106 of them when they sold, excuse me, when they spent $5,500 on advertising. Okay, well, maybe they don't want to sell 106. They want to sell more. They want to get up to at least 124 of whatever they're selling. How much would it take to do that? Well, you can kind of see in pencil I did this. Okay, here's 124. And so I took my pencil and I kind of went over here and I hit the line. And I said, okay, when is that going to be? And I don't know, right about here. That might be $6,800 maybe. I think when I wrote it in pencil, let's see what I said. I said about $6,750. It's probably a little bit beyond that. And so we might update that to say instead, maybe more like $6,800. Okay, so it's just an estimate, but the line allows us to make that prediction. If we didn't have a graph, we couldn't make a prediction. And we want to be able to say, hey, if you spend this much money, you can actually sell 124 of them, whatever you're trying to sell. When we talk about line of best fit, some important things we talk about are the y-intercept. And remember, the y-intercept is where it hits the y-axis, and that's what we just talked about. Another important thing to talk about is the slope of the line. And so that shows us, what the rate is. And the way we talk about slope, remember that slope is rise over run. And if we look at our rise here, in our situation, on the rise, we have sales. And on the run, we have dollars, specifically $1,000. So if we were going to interpret the slope, if the slope is 12, then we would say 12 sales per $1,000 in ads. Okay, whenever we talk about slope, we always talk about per. So it's 12 sales per $1,000 because that's what the slope is. The y-axis is sales, The x-axis is thousands of dollars. Let's look at another one. The data in the graph below shows the resting heart rate and the ages of a group of 20 people at the gym. Use the scatter plot to answer the following questions. Okay, I drew in my line of best fit. I honestly think it's not the best line, but it's pretty good. I'm just thinking I kind of feel like it needs to be a little bit more like this. But again, it's pretty good. There is an observation at 4560. This is a coordinate, 4560. Can we find 4560? Here's 45. Here's 60. Where do the 4560 is that person right there? What does that dot represent? That dot represents a person. And it's a person that was at the gym, and we took the resting heart rate. That person was 45 years old. See, this is years. And they had a resting heart rate of 60 beats per minute. Okay, that's what this coordinate right here means. If we say 4560, that's a person, 45 years old, 60 beats per minute. Okay, part B, sketch in the line of best fit. I already did that, but why don't you take a second to find a ruler or a straight edge and sketch in a line of best fit. And our lines are going to be close to each other, but they're not going to be exactly the same, and that's okay. Okay, estimate your y-intercept and what it means in context. Do you remember where the y-intercept is? The y-intercept is here, wherever it hits the y-axis. It's just about 75. I think when I wrote my answer, I was using, do you see that pencil line? I was really just, I didn't even use a ruler. I was just really sloppy with it. So what it means is, at age 0, which isn't that weird, it's like, what does that even mean, age 0? I guess at a baby. The baby's resting heart rate would be 80 beats per minute. Or in this case, actually, let's update that to say 75. So a baby would have a resting heart rate of 75 beats per minute. Is that true? I have no idea. That's just what the graph, according to this line, says. Sometimes age does not follow a linear pattern. Like think about when babies first grow, they grow a lot in that first couple years, right? And then it slows down. So it's not linear. But this one might be, I don't know. The next one says, estimate the heart rate of someone who is 65 years old. Well, we look at our table or our graph, and 65 is not even on there. And so that's why I made this little pencil line. I'm like, okay, this is 50, 55, 60. Maybe this is 65 right here. And so if I go up and I estimate where does that hit? Well, right there, where's that? I don't know, maybe about 50 or a little bit over. Okay, so the resting heart rate of someone who is 65 years old is about 55 beats per minute. Okay, it's just hard to see. Maybe even lower, maybe more like 52. I can update that, about 52, somewhere in there. Depends on where your line is. Your line might be a little bit different. And remember how I adjusted that line at the beginning? So that might have been a little bit different. But that's what a graph allows us to do. If we can graph a scatter plot, we can get some data, we can make some predictions. And even though we didn't find someone at the gym who was 65 to plot their resting heart rate, well, still we can predict what it would be. And again, there wasn't a baby, but we could predict it if we had a line, okay? So that's what the math allows us to do. Let's turn the page. Okay, there are some ways you can find a real line of best fit. And by real, I mean like right now, we're just like taking a ruler and kind of guessing. But there are computer models that can help us do that, calculators and things like that. And we will probably do that together in this class. But another way is you can take a statistics course. There is a course here at school that is called statistics. And you can take that course and you can learn all about this. Okay, but for now, we haven't learned that yet. So I'm just going to give you the line of best fit. So this one is given to us. Let's see what's going on. The graph shows the oxygen consumption compared with how long it takes a person to run 1.5 miles. Take a moment to make sure the display really makes sense. The equation of the best fit line is this. Okay, when I did that, take a moment to make sure the display makes sense. It didn't make any sense to me. The reason why? I'm like, oxygen consumption, what does that even mean? I had to Google it. What it means is how many milliliters per minute you are consuming, like how much oxygen you're using every minute. That's what it means. So go ahead and add that to your y-axis so you understand what it's talking about. Okay, using the graph, predict how much oxygen is consumed if someone runs 1.5 miles in 6 minutes. That is a world record pace. Okay, I'm going to look at my graph and I'm going to look for 6 minutes And oops, 6 minutes is not on my graph. It would be like way back here, but I don't know where it is because it's not on the graph. So if it's not on the graph, we can use our algebra skills to figure that out. And the 6 minutes, do you see how it's here on the x-axis? The time is on our x-axis. So we can plug in a 6 in for our time on our x-axis, and we can plug it in for x. So let's do that. I'm going to plug this in. I'm going to put it into my calculator. I'm going to see what I get. Put that in your calculator and see what you get. Okay, I got 62.56 milliliters per minute. So if you run a 6 minute, 1.5 miles, which is a world record pace, you're going to be going through 62.5 milliliters every minute. That's a lot. Okay, well, what if you're not a world record minute and a half, or a mile and a half? What if it takes you a little bit longer, like about my pace, about 17 minutes probably for a mile and a half? I'm not even sure if I can run that fast. So to do that, once again, we're going to take that 17 and we're going to plug it in for x and we're going to work it out. And so take a second to put that in your calculator. Okay, I put that in my calculator and I got 26.15 milliliters per minute. Look how much less that is. The person who's running fast is using a lot more oxygen than this person. Does that make sense? I think it does. That person who's running fast, holy cow, they are huffing and puffing. This person, they're like having a leisurely jog. They're not huffing and puffing. So they're not using as much oxygen per minute. Okay, so what if we ask a different question? This one asked, 17 minutes or 6 minutes. What if we asked a different question? We said, well, how much time does it take if they consume 30 units of oxygen? Well, one thing we could do is we could look at our graph. And so if I do that, 30, oh, it's way down here. We're not going to find it, are we? We could maybe like extend our graph and take a guess. If we extended our graph and took a guess, can you see that might be like about 16 or so? Okay, but that's with the graph. Instead of using a graph, we can use our algebra skills. And so we can use that same equation, except this time we don't want to plug it in for x, do we? This time we want to plug it in for y, because y is the oxygen consumption, and they're talking about oxygen. So this time let's put the 30 over here and solve this. Do you remember how to solve this? I know you do. We're going to subtract 82.42 from each side. And when we do that, we get negative 52.42. And then we have negative 3.31x over here, so we want to divide by negative 3.31. And that's going to give us about 15.8 minutes. Look how close that is. 15.8 minutes compared to 16, that's pretty close. So our algebra can allow us to solve it even more precisely. I had to say about 16 minutes, but yet I can do the equation and get a much better answer. This next one is just another example of the same type of thing. We could plug in 65 over on the left and we could solve it by subtracting 82.42 and then dividing by negative 3.31, and we would get about 5.26 minutes. Okay, but another important thing is slope. And in our equation, let me go back up to the top. In our equation, our slope is negative 3.31. And this question is, what does that slope mean? Remember, we're talking about rise over run. Rise, oxygen, run, minutes. And so when we talk about that, we say negative 3.31 oxygen per minute. That doesn't really make sense. What does that even mean? Well, I typed out another sentence of what I really would say. I would say for every minute slower that a person runs the 1.5 mile, the oxygen consumption drops 3.31 milliliters per minute. So you're dropping oxygen every minute. You're not using up as much oxygen as you were. And it's negative because that's the slope is negative, so it means you're losing it. Okay, when we get to class, we are going to be doing an example of this, and you're going to create your own scatter plot and take a look at what that data means.